Okay. Good news. The recording worked. So we can keep going, and hopefully I don't have any more issues. Anyways, multiplying polynomials. We might just go straight into the other section, which is 10.3, the special patterns. If this is like under 30 minutes. If I finish this in like sub 10, I think we should be fine. Anyways, multiplying polynomials. Don't worry about this, but just know that we will be using the distributive property. For example, if we have 3x and we're multiplying this polynomial with it, we have to just multiply them individually. 3x times this, times that, times this, and whatever we get as an answer will show up here. But there are times where we have to use the distributive property twice. For example, if we have something like a plus b times c plus d, we will do the multiplication as so, where we have a times c, a times d, and then we will also then do b times c, b times d. And this is what it will look like when we break it down. For example, a is multiplying everything c plus d, and b is multiplying everything c plus d as well, and then you should do it one more time, right? And you should get something like this. A times C, right? So AC, A times D gives you AD, B times C gives you BC, and B times D gives you BD. And then if you were to add all of them together, it should look something like AC plus AD plus BC plus BD. This same rule that we have here can also be applied if any of these polynomials were like subtracting. So a, let's say for example, a minus b or c minus d could still work. This is just showing us the way to distribute each of the terms in our parentheses. For example, if we were to solve this problem, x plus 2 times x minus 3, we'd solve this like so, where we have, let's say for example, our first break would be x, this first x times all the terms inside here, or might look something like x times x minus 3, plus the second term 2 times all this stuff, so 2 times x minus 3. From there, we'll go ahead and distribute one more time, so it looks something like x times x plus x times negative 3 plus 2 times x plus 2 times negative 3. Then we just solve. X times x, in this case, since we are multiplying two variable terms, what we'll do is we'll just add the exponents, the powers, right? So 1 plus 1, this gives you 2. From there, x times negative 3, we should just get something like negative 3x, since we can't really combine them, but we just kind of smush them together, and it should be okay. From there, we also have 2 times x, same thing, smush them together, we get 2x, and 2 times negative 3 gives us something like negative 6 as our answer. From here, we can still combine some like terms. For example, negative 3x plus 2x, we can add these together. This gives us something like negative 3 plus 2 gives you a negative 1. So your final answer should look something like x squared minus x minus 6. Which is okay. I think this question wasn't too bad. We'll just move on. This same method though, real quick, we will break this down into something that's a little bit easier to understand. We'll use an acronym called the FOIL pattern, FOIL, which stands for first, outer, inner, last. It looks something like this, and you can kind of see where I was going with our first example. I didn't really like how, honestly, once you learn how to do the FOIL pattern, you'll always use it. So we're really just taking the first terms and multiplying them together. So for example, 3x times x, this gives you x squared. The outer terms, so let's say for example, this 3x and this 5 will multiply together. 3 times 5 gives you this 15. The inner terms, so inner terms looks like this, the 4 and the x. So 4 times x gives you 4x. And finally, the last terms of each of the polynomials, 4 times 5. 4 times 5 gives you 20, and then we just combine. So it's a little bit more of a streamlined way to solve the problems, I think, especially when they look like this, because it's all just patterns that we're really looking at. Um, so let's try that real quick. First, outer inner last with this. Whoops. Yeah, yeah, this is fine. Anyways, first outer inner last with this problem, we're just taking 3x and multiplying it with 2x first. 3, I'll just write it out so it looks a little bit nicer for us to look at. 3x times 2x. We'll then work with the outer terms. So in this case, it's 3x times 1. So 3x times 1. We'll then work with the inner, or FOIL, F-O-I, inner terms. So negative 4 times 2x should look something like negative 4 times 2x. And last but not least, we also have this last terms are negative 4 times 1. So negative 4 times 1. And we'll just multiply all these terms together. 3 times, I'm trying to pick a color that we didn't use yet. 3 times 2 gives you 6. X times x gives you x squared. 3x times 1 just gives you 3x. Negative 4 times 2x. Negative 4 times 2 gives you negative 8. Then we just write the x right next to it. And negative 4 times 1 gives you negative 4. From there is still some more simplifying to do, which in this case, we're just going to go ahead and combine 3x minus 8x. 3 minus 8 gives you negative 5x. And we just drop down the negative 4 at the very bottom, or minus 4, giving us our answer here. Same thing that happened here. Basically, the book, or the high school book, just showing us what we did when we did the FOIL method, which wasn't too bad. Yes, true. To multiply two polynomials that have 3 or more terms, remember that each term of the polynomial must be multiplied by each term of the other polynomial. Use a vertical or horizontal format. So what are we talking about here? Vertical or horizontal format to multiply them, right, is what we're trying to figure out here. Using the vertical format to solve this type of problem is, in my opinion, not the best way to do things. I like doing the horizontal method, which we'll go ahead and showcase here. But vertical still kind of works out for us. Just might be a little bit interesting to do. Doesn't really matter if we do it, or rather if the polynomials are written in standard form or not. But in this case, I'll just go ahead and rewrite this 5 plus 3x minus x squared in standard form, which should be negative x squared plus 3x plus 5. And so if we remember us solving a problem vertically, like adding or subtracting, for example, 10,000 minus 5,000, we get something like just, subtracting the zeros, and then for the last part, 10 minus 5 gives us 5. So 5,000 should be our answer. Same concept will work if we're doing multiplication. For example, 10 times 11, right? 1 into 0, we get 0. 1 into 1, we get 1. 1 to 0, we get 0. 1 to 1, we get 1. Then we just add. 1 drops down. 1 plus 0 gives us 1. 0 plus nothing gives you 0. That's your answer here. You'll get the same kind of thing if you solve this kind of product vertically, but it is kind of weird to solve. For example, if I were to set this up to multiply this vertically, it will look something like negative x squared plus 3x plus 5 times our x minus 2. So we're still keeping in mind what terms go where, right? Making sure that they line up nicely. But when we go about multiplying them, this is where it gets a little bit tricky. For example, if I were to multiply our first term, I'm not doing, let's say, for example, this 1, or rather this -2. Um, actually, I think we should. So we'll take this -2 and multiply it with the terms inside our big polynomial. So -2 times 5, this gives us something like -10. -2 times 3x gives us -6x. And -2 times -2, or x squared, gives us a positive 2x squared here. We'll do the same format with x. So multiplying x with all these terms here, we'll first start with the small one. X times 5 gives you positive 5x. X times 3x gives you 3x squared, and we ought to make sure that this is also positive. And finally, x times -x squared gives us negative x to the third power. Then we'll just drop everything down and start adding them. -10 plus nothing is -10. Negative 6x plus 5x gives you -1x, or just -x. 2x squared plus 3x squared gives you 5x squared. And finally, negative x to the third power is just negative x to the third power, giving us our last term here. Vertical method, I like it. Not really. I like the horizontal one better. But like I said, you can use any way you want. This way might be a little bit confusing, especially the setup time for it. And that's why I like the horizontal method a little bit more, because it's pretty straightforward. In this case, how do we solve a problem that looks like this horizontally, right, is the question. And so what we're doing here is basically taking each of these the terms inside our small parentheses here, a small polynomial here, and multiplying it with, basically each of the terms in the bigger polynomial. But how would that look like? If we do this horizontally, it may look similar to what we saw in our first slides. It might look something like, for example, 4x squared times 2x minus 5 plus negative 3x times 2x minus 5 plus -1 times 2x minus 5. Then we'll just solve, right? Or rather, multiplying them and then solving by combining like terms. So in this case, if we're multiplying, let's say our first group here, we're taking 4x squared and multiplying with all the terms in here. So 4 times 2 gives you 8. X squared times x gives you x to the third power. 4 times -5 gives you -20. X squared times nothing is just x squared. -3x is our next term that we'll go ahead and multiply with the terms inside the small polynomial. So we'll take -3x, multiply this with 2x. This gives us a -6x to the second power. -3x times -5 gives us something like a positive 15x. And we'll move on to our last term, which should be 1. Maybe I shouldn't use orange. I'll use a dark blue. -1 times 2x, and -1 times -5. -1 times 2x gives us a -2x. -1 times -5 gives us a positive 5. From there, we're not done yet. Unfortunately, we have to make this simplify this. And so we have to start adding all the terms that can be added together. For example, we can add this term with this 6x squared, and also this 5x with this -2x. And so we just combine. We have our 8x to the third power, -20x squared plus -6x squared. We get something like -26x squared. 15x minus 2x gives us 13x. And finally, 5 can't be added with anything, so we just say plus 5 here at the very end, giving us our final answer here. Yeah, that's it. I like this method a little bit better because it looks more similar to what we're going to be using more than half the time, the FOIL pattern or FOIL method. And it's more intuitive if you start to appreciate the FOIL pattern a little bit more. In terms of that, this kind of ends off our multiplying polynomials, which means we can kind of hopefully streamline through the next and last section, special products of polynomials. Um, the last lesson we just had, we know that we can use a FOIL pattern to do these things, but there's special patterns that we'll see, like special products that we'll always recognize to be like ways to solve them. Like if we have like a template to use, yeah, basically to use, we can always just replicate answers in that way. Um, yeah, that obviously did not make any sense at all, but if we go to the next slide, hopefully it makes a little bit more sense. So there's two patterns that we'll go ahead and showcase. The first pattern is the sum and difference pattern, where we have a plus b times a minus b. This will always give us something like a squared minus b squared, which you can see in the example right next to it. And from there, we also have something called the square of a binomial pattern, which is going to be a plus b squared is always going to be equal to a squared plus 2ab plus b squared, or the alternative route, if instead of plus, it's minus a minus b squared, it'll always look something like a squared minus 2ab plus b squared. And the examples are as follows here on the right side. And so if we have something like this product, for example, we notice that it fits something like, let's say, for example, our first term is going to be a, our second term is going to be b. This is just a minus b times a plus b, which fits the sum and difference pattern, which means I will always get an answer that looks like a squared minus b squared. And we'll go ahead and showcase that first. So if we just take our a term, which in this case is 5t, we'll just raise 5t to the second power and subtract it with our b term, which is 2, and raise it to the second power as well. This gives us an answer that looks like 5 squared is 25, t squared is just t squared, minus 2 squared is just 4. And this should be our answer. Just to prove this though, real quick, we can also take the same product and use the FOIL pattern to solve, and we'll still see that we get the same answer like what we have up here. 5 times 5t gives you 25t squared. 5 times positive 2 gives you a positive 10. Negative 2 times 5 gives you a negative 10t. And negative 2 times 2 gives you a negative 4. We notice here that 10t minus 10t just becomes 0, which means you get your final answer, which is just like what we got here up top. 25t squared minus 4, same thing. They equal the same thing. So think about it this way. If we remember all of these patterns, the sum and difference pattern and the square of a binomial pattern, it will make our lives very easy in terms of figuring out, what does it simplify to, and even the reverse method, right? Like factoring, which we'll get in a little bit later. But using these patterns, we'll go ahead and solve the next couple examples. For example, in letter A, if this looks like the square of a binomial pattern, but with the plus, this means that this, letter A, follows the pattern a squared plus 2ab plus b squared. So all we need to do is just substitute our a terms with whatever a is. In this case, it's going to be 3n, and b for whatever b is, which in this case is going to be 4. Oh, this should be b. Whoops. So how does it look like? It will look something like 3n squared plus 2 times 3n times 4 plus 4 squared. And then we can solve. 3n squared gives you 9n squared. 2 times 4 is 8. 8 times 3 is 24. 8, 16, 24. Yep, 24n. And 4 squared is going to be 16. There you go. Final answer. Same thing for B. B will use the same pattern, but the negative version. So in this case, it should look like a squared minus 2ab plus b squared. And then same thing, we just substitute a and b for whatever they are in here. In this case, a is 2x and b is 7y. So substituting all of that, we get 2x squared minus, 2 times 2x times 7y plus 7y squared. Something interesting happens here because the middle portion is going to give you something interesting, and we'll explain that in a few moments. But 2x squared gives you something like 4, right? Because 2 squared is 4. X squared is x squared. From here, the middle side of this are negative 2 times ab. Something peculiar is here. Two different variable terms, x and y. And so what should we do if we have two different variable terms? The easiest way to explain this is we have to label them from, alphabetical order, right? X, then y. But what we'll do in terms of like the math side, the number side, is just multiply the coefficients of each of the terms. So negative 2 times 7. Negative 2 times 2 gives you negative 4. Negative 4 times 7 gives you negative 28, right? 7, 14, 21, 28. Yeah, 28. So negative 28. And then we write our x term first, right, alphabetically, then our y term. And last but not least, 7y squared. 7 squared is 49, and y squared is just y squared. Should give you our final answer. This special case here in letter B, the middle portion, you'll have more examples that look like this in the future, but for now, just know that work with the coefficients only and any kind of constants that we're working with, especially when we're multiplying. And then when we want to write out the variable terms, we write them out alphabetically from, A down to Z, whatever. And that's it. Very short. 2 videos for the most part. The next video that you'll probably be watching after this is factoring. I definitely didn't go over all that I could have went over in terms of this, but at the very least, the things I did go over will definitely help you out with the pre-test. You'll start to see that a lot of the questions and the things that I'm, showing you guys will definitely translate heavily to what you see in the placement test at the very least. Anyway, just wait for the next video.